All right, good morning, everyone. My guess is we're going to be watching this in class, I think, the first one at least. So, this is the beginning of chapter 8. Now we're going to section 8.2. We've already done 8.1 and 8.3. Section 8.2 is long section. It's all the basic foundations of hypothesis testing. It'll take us 3 full lessons and 3 full days. So it's hypothesis testing. So you see on my screen, test of significance or hypothesis test. So sometimes we call it a test of significance. Sometimes we call it a hypothesis test. It's the same thing. The idea is very simple. We think something to be true about the population. So once we pick that thing, whatever we think is true, then we're going to take a sample and we're going to test our sample against what we think. So you can see here on my thing, comparing the results of a sample to some predetermined standard. So let's say I believe that the proportion of students at Mountain View High School who left town for Thanksgiving last week was 30%. That's my guess. Okay, so now I take a sample. I could use you guys as a sample right now. Maybe I will even, who knows? And then what we're going to do is this. If I take my sample and the sample is kind of close to 30%, we're going to say, okay, maybe I was right. We're not going to ever say I'm right, even if it's 30%. We just can't say I'm right because that was just one sample. So hypothesis tests can be a little bit weird for some people because we never really say that our hypothesis is true. We only say that there is no evidence that it's false. Okay, so we might say it's false. We might say there's evidence that it's false. We also might say there's no evidence that it's false. Not exactly the same thing as saying it's true. But if it's close to 30%, then there's no reason to conclude my guess doesn't hold. And if it's a long way away from 30%, let's say it's 60%, then whoa, oh my gosh, no way, you're not right. So if the difference is large enough, then we conclude the standard doesn't hold. So that's kind of the basic idea. It's going to take quite a while to get the formal language of all this. We're going to be very informal at the beginning. Okay, just kind of like informal discussion. So a little terminology for you here. It's called statistically significant. People use this term all the time. I don't think they know what it means. Most of the people, they'll say, yeah, this result is statistically significant. Well, what does that mean? Statistically significant means that a sample proportion is statistically significant if it's not reasonably likely when the proposed standard is true. Okay, so we're going to do just proportions right now. We'll do other things too, means and stuff like that. But right now, we're just going to go for proportions. Okay, so here's an example. Let's say I believe there's 50% heads in a proportion. Clearly there is, but let's just say we believe it. But if I flipped a coin and I got like 10 heads in a row, you would say, whoa, that's not very likely to happen, right? This would what we would be called a statistically significant result because we think it's 50%. 10 heads in a row is way too far away, not reasonably likely. We'll go through that math again. We probably just actually did before this video today, I hope. We probably conclude that 50% is not the true proportion, right? So then the idea is which ones are statistically significant and which ones aren't. And the way we do that is just reasonably likely. We go back to the old things we've done. In other words, if we think, I hate to use only 10 flips, but let's say I use 40 flips, we think the proportion is going to be 0.5. The standard deviation would be 0.5 times 0.5 over 40. If we're doing 40 flips in this case, 10 is not enough flips. That's why I use that. And then we can figure out reasonably likely, right, by doing inverse norm of 0.025 with a mean of 0.5 and a standard deviation of 0.5. I'll do the one side. Actually, I can do both sides because it's going to be symmetrical, right? So if I go inverse norm, 0.025 with a mean of 0.5 and a standard deviation of 0.5 times 0.5 divided by 40, I get 34.5%. So if I go the other side, what is that? 15.5, so 0.655. I hope I did that right. So anything, if I were to flip a coin 40 times and get over 65%, I would say that's a statistically significant event. So statistically significant specifically means not reasonably likely. But that's a lot of work, right? So, if I flip that coin or if I have a guess and it's not 40, I'd have to do this every time. So we're going to look for a little shorter way and then having to figure out which ones are reasonably likely. And then did I get something that's reasonably likely or not? Okay. So we're going to try to shortcut that a little bit. It's really just too far away from the mean, right? Is the idea, if you notice, right? Too far away. That's 2 standard errors, right? About 2, or it's 2. It's like 1.96, but it's about 2, right? So we're just really talking about getting too far away. All right. So one of the things we're headed towards, not today, but later, is formal language. So there's going to be some things you need to know, some terminology. P, we've already talked about P, is the true population proportion. For the most part, we don't know what that is, like really ever, right? P hat is the proportion in the sample. Here's the new one. It's called P naught. P naught, P sub 0, P naught. This is the hypothesized value of the population proportion. It's called the standard. It's what we think is true. It's our guess. So let's just do this example, right? Let's say we flip the coin 40 times and we get 10 heads. Now, if you go back to this, 10 heads is 25%, right? 10 out of 40 is 25%. So you can see we're out here, right? To the left of the 34.5%. So it's not reasonably likely, but we don't want to have to do this math right there all the time beforehand because it's a lot of work. So we just want to figure out how many standard deviations away is it? That's all we're doing. If it's more than 1.96 standard deviations away, then it's statistically significant, okay? So here's the math. How do we check this, right? So 10 heads means we got 25%. We think our proportion is 0.5, right? So what we do is we write up a little normal curve. That's our population. And the mean is 0.5. The standard deviation would be 0.5, just like it was on the last problem, right? Over 40. But we're not going to do reasonably likely. What we're going to do is just find the z-score, right? The same way we did way back in chapter 2. We're just going to find that z-score. So you find the z-score the same way we found it before, which is p hat, what we got, the x, minus p naught, which is the mean, what we think is the mean, which is 0.5 in this place, divided by 0.5 times 0.5 divided by n. So the same exact math we just did on the last page, except for I don't have to go through the reasonably likely. I just have to figure out that score. It's called a test statistic. So if I do it for this problem, it's going to be 0.25 minus 0.5 over the square root of 0.5 times 0.5 divided by 40. Give me a second here. It's going to be negative, right? Negative 0.25 divided by the square root of 0.5 times 0.5 divided by 40, negative 3.16. Remember, we knew it was going to be way out here, right? It's 25%. Okay, so basically what we've learned is we're way out here at negative 3.16, too far away, right? Past my reasonably likely cutoff. So notice I don't have to find the value of the reasonably likely cutoff. I could. And then I could just see if 25% is to the left of it, but it's a lot easier to just find that z-score and then go from there, okay? So the idea of statistically significant, though, is only good for 95%, right? Because we're using the term reasonably likely, statistically significant, 95%. So we could use other values. Mathematicians, just like for confidence intervals, we don't have to use 95%. We could use 99, we could use 90. So these are called critical values and level of significance, all right? When we reject a standard by saying it's a rare event or not reasonably likely, we're using the idea of 95% or the cutoffs of 1.96 and negative 1.96. Okay, but we could change these. So here's some terminology for you. We have a thing called level of significance. Okay, the level of significance is called alpha. You see my alpha there. If it's 9, it goes along with the confidence. So the confidence level is the 95%. The alpha is, let me write on here, what's left over on the side. So like half alpha here and half alpha there. Ooh, that looks bad, sorry. Half alpha. 2.5% on each side, okay? So the alpha is called my level of significance. The alpha and the confidence level always have to add up to 100%. So if your confidence level is 90%, then your level of significance is 10%. It's the outside area. They have critical values that go along with them. These are called z-stars. Z stars. Okay, there's called critical values. For 95%, it's 1.96. The most common ones, of course, are the 1%, 99%, which goes along with 1%, which is plus or minus 2.575. Okay, and then the 90% or the 10% alpha is plus or minus 1.645. Those are the cutoffs, right? If my test statistic is too far outside, then we would reject what we think to be true, and we'd say it's wrong. If it's inside, we would say, nah, there's no evidence that I'm wrong. Notice I didn't say I was right. It's just too close. So there's no evidence that I'm wrong. Okay, we could do other percents. So every once in a while, you might get a 4% or a 5% or a 6% or something like that. Then we could find those using inverse norm. The smaller the level of significance, notice, the farther out we get, which means it's harder to reject. It's harder to say that wrong, okay? If it's not stated in a problem, alpha is always 5%, which means your critical values are plus and minus 1.96. They'll give you a question and say, is there evidence that you're wrong? Pretty vague, right? But that means 95%. If they want to change it, they'll change it in the problem. Often they don't say anything, so it just gets left out. So we'll do a couple of examples here, I hope, now that I'm done, and we'll go from there.